Okay. All right. Hey, everybody. Thanks for joining another EERI seminar. Today, we've got Mohammed Hussein. He's the Executive Vice President of GRL Engineers and the Executive Director of Global Industry Relations at Pile Dynamics Incorporated, which is the world's oldest and largest specialty deep foundation testing services and testing equipment manufacturing companies, respectively. Over his more than 40-year career, he's consulted on over 1,000 deep foundation projects across the majority of the US and multiple countries. He's frequently organizes educational courses and seminars on deep foundations, including ASCE's continuing education class on deep foundations design, construction, quality control. Mohammed is a member of the Deep Foundations related committees of the DFI, ASCM, PDCA, ASE, and TRV. He has chaired the ASCE's Geo Institute Committee on Deep Foundations and the PDCA's Education Committee. Currently chairs the PDCA's Technical Committee. He's also received multiple professional and industry awards and recognitions. He's also done over 60 technical papers and co-edited 10 engineering books, expert level on PDCA/PDI dynamic measuring and analysis proficiency test, and foundation quality assurance testing, and is a registered professional engineers in multiple states. He also conceived and chaired the first International Foundations Congress and Equipment Expo, which has been periodically repeated, and is now an industry landmark. So with all that, we're very excited to see you, Mohammed, and please take it away.
Thank you, Noah. Thank you very much. Thank you for the introduction. And hello, everybody. And thank you for checking in and signing in into today's presentation. I hope you will find it interesting, and I will provide you some information that hopefully is useful to you as well. So the presentation will be about deep foundations, their different types, and testing methods for geotechnical load-bearing capacity and structural integrity evaluations. Deep foundations have been used since antiquity. Herodotus mentioned driven piles 2,500 years ago in his writings. In fact, we still have structures nowadays that are hundreds of years old supported on deep foundations. One may say that deep foundations are what make our civilization possible by allowing us to build all of the structures needed for a modern civilization living. In today's practice, deep foundations are used to support all types of structures and all kinds of geotechnical conditions to resist all kinds of load combinations. Deep foundations can be divided in a variety of ways. I will divide them today into three major categories, including driven piles. And by the way, there is a 3-volume manual design and construction of driven piles available to you for free that you can download in PDF form from this website, fhwa.dot.gov. At the end of the presentation, I will indicate to you my email address. If you'd like me to, I can send you a link to all of what I'm going to suggest to you today. So we have driven piles. We have auger cast piles that are a type of cast in situ foundation. There's also a manual for that you can download. And drilled shafts. So these are the three different types of deep foundations I will be talking about today. There is a 2-volume drill shaft manual as well that you can download from the website. Driven piles consist of wood piles, timber piles, concrete piles, and steel piles. Timber piles are typically used to support lightly loaded structures. And there is another manual here you can download for free on the internet of the design and construction manual of timber piles. Steel piles come in 2 varieties, H-section and pipe piles. There are about 20 different standard H-pile sections available for use. And there are design tables to assist you in the design of these different sections and cross sections of H-piles. Steel pipe piles come in a variety of sizes, ranging in diameter from a few inches to a foot or two, to maybe 5 feet, to more than 10 or 15 feet. So they range in size, diameter, wall thickness, and length as needed. Concrete piles are typically pre-stressed concrete piles, have a strength of about 6,000 psi, compression strength, or they can be post-tensioned and they may have a strength of maybe 10,000 psi. The newest development in concrete piles is the use of ultra high performance concrete in driven piles, and the strength of which can be upwards of 25,000 psi. Piles can also be composite and variable in sections. They can be different combinations of steel and concrete and can have highly variable profiles depending on the need for the foundation design and the loads they're supposed to support. There are hundreds of different pile driving hammer models available to install to drive these piles into the ground, and they can operate by hydraulics. We may have hydraulic hammers, air hammers, diesel hammers, single acting or double acting. So there's a variety of different options available for the driving of these driven pile foundations. So we drive piles individually into the ground, typically in a group. So we may drive a group of piles to support the structure we're trying to support, to found. So this is a pier foundation, and this may be a building. So we will drive a whole lot of piles, large pile groups to support the various structures. During pile driving, the pile undergoes or resists, the soil resists pile driving by dynamic pile driving resistance dynamically. However, when we use the pile as a foundation unit, we need its static load bearing capacity. And there is a difference between the static load bearing capacity and the dynamic pile driving resistance to driving. So the best way to evaluate the static load bearing capacity after we have driven a pile is to actually perform a full scale static load test, as we see in the picture on the right. So we can perform a static load test by using dead weight to put on top of the pile to see how much it will be able to support statically. Or we may use reaction piles to support the reaction beam. So we put a reaction beam on top of the pile, we put the hydraulic jack, and then we load the pile hydraulically, and we measure the corresponding load and displacement. So incremental load and corresponding displacement. And this is a typical plot of a static load test. Please keep in mind this relationship of load and deformation, load and movement at the pile top from a static load test. I will come back and revisit it in the middle of the presentation. So while static load testing is the best thing we can do to evaluate the static load bearing capacity of the pile, it is a very time consuming process. It's very expensive. It may cost 100,000, 200,000, or maybe 500,000 or more to perform a static load test. And in some cases, it's just physically impossible to do. And others may require numerous of these tests on the project. So there are limitations to that approach. So what we're trying to do then is to try to find a relationship between what is the static load bearing capacity from the dynamic pile driving resistance. In other words, we will try to relate the driving resistance of the pile penetration into the ground as is typically measured by blows per foot or blow count of pile driving, and the tons, the static tons the pile will be able to support in service. More than just trying to find a relationship, we want to have an equation of however many blows per foot it takes to drive the pile into the ground and how much tons it will be able to carry. This is a nonlinear relationship that we will try to quantify now. It has been known for a long, long time, since antiquity, that the more energy, the more work it takes to drive a pile to the ground, the more the pile will be able to support. If a pile goes down to the ground easy, as opposed to being very hard to drive, then the harder to drive, the more load it should be able to support. So that is kind of a common sense feeling that in 1870, somebody called a Mr. Wellington tried to formulate and equate the work it needs to drive a pile and the resistance the pile will be able to support. So this is called the energy approach. If we know the weight of the hammer, W, the drop height H, and then we hit the pile with the hammer, it penetrates a given distance into the ground S against a resistance R, then we have equilibrium. So we have a relationship WH equals RS, so we can back compute R, which is the resistance of the pile to pile driving. This is actually pile driving resistance, not the static load bearing capacity. So a lot of people try to improve on that very simple relationship from the 19th century technology, and there are many, many of these on record, like 400 of these on record. They are nothing but a variation of the same approach. Some of them can look complicated, but really not very much improvement over the basic equation. So not very good to use nowadays in the 21st century. So let's try to look further into what does happen when the hammer hits a pile. What are the fundamental mechanics of pile driving? And it has been realized that pile driving follows the process of wave propagation, one-dimensional stress wave propagation. So when the hammer hits a pile top, a compression stress wave travels elastically in the pile back and forth at a very high speed, like 15,000 feet per second. And Mr. Smith in the 1940s realized that and wrote a computer program called the Wave Equation Analysis of Pile Driving. In fact, this computer analysis that Mr. Smith wrote was the very first application of digital computers in civil engineering. Mr. Smith wrote this program to be used in-house in his company called the Raymond Pile Driving Company. And later on, the United States government commissioned a group in Ohio, which later became the GRL group, my group, to write a public program for the analysis of pile driving using the wave propagation principles. So the WEAP program or GRL WEAP program is a simulation program using numerical analyses that follows the stress wave down the pile and the resistance against the soil resistance against pile penetration, and comes up with this relationship of blow count and static load bearing capacity by taking care of the dynamics of the soil resistance damping effects. So for any pile drive, for any capacity we need for the pile to support, for any design load times the factor of safety, ultimate capacity, this equation, this program will tell us how many blows per foot we need to continue to drive the pile to reach it and to achieve resistance. That is what the inspectors use on the job site as a quality control and quality assurance to pile driving to make sure that the pile reaches the required blow count that achieves the required resistance. However, being a computer program, a simulation computer program, it relies on assumptions. And there are a bunch of assumptions one have to assume and plug into the program to come up with results. Although it is a very powerful program, but its reliance on assumptions means that it has potential sources of error. For example, hammer performance. We have to assume a certain level of hammer performance in order to make sense of the hammer driving blow count as it relates to soil resistance effect. Because a blow count is not only a function of resistance, it's also a function of hammer performance. So if we are off on the assumption of hammer performance, therefore we will be equally off by relating the blow count to that static load bearing capacity. But that's something that has to be assumed. Soil pile interaction has to be assumed as well. And I can give you a simple example, such as the open-ended steel pipe pile. When we drive an open-ended steel pipe pile into the ground, it may act like a cookie cutter or it may plug. Either case will have a very different relationship of blow count and load bearing capacity. We don't know if the pile is going to plug or not, but we have to assume that ahead of time. Because of all of these assumptions needed, then there are potential sources of error in the analyses. So instead of assumptions, what if we were to go out on the job site and take measurements? We will measure what we need to know, analyze it, and come up with results. These measurements are typically done with a computer unit on the job site called the Pile Driving Analyzer, PDA, and the analyses are done with a computer program called CapWeb, which is a wave equation analysis based on the measurements on site. So let's start from the very beginning. Again, this is a static load test. We need all of this dead weight, all of this weight, all of this load to statically load test a pile with. We need dead weight. What if we were to think a little bit outside the box? What if I was to take a very small portion of that dead weight for the static load test, a small percentage of it, put it in a guide, lift it up high enough and drop it in such a way that that will give me the same load on the pile as all of that dead weight load. So both of these processes, both of these procedures can give me the same load on the pile. So therefore, if I can take a small piece of that, I don't need that whole weight. I can dynamically duplicate or replicate the load testing effect. As a matter of fact, I don't have to do any of that. This is being done for me for free. It's called the pile driving hammer. So the hammer, as it pounds the pile to the ground during pile driving, is loading the pile with every blow. All we have to do is to put some instruments on the pile and take measurements during pile driving. This is what constitutes a dynamic load test. So this is dynamic load testing versus static load testing. This dynamic load testing is standardized by ASTM through ASTM standard designation D4945. So dynamic load testing, therefore, is nothing but taking measurements on the pile under the impacts of the hammer during pile driving. These measurements consist of a strain transducer measurement, measuring the strain and therefore the force, and accelerometer. So we need two units, a strain gauge and an accelerometer. The strain gauge measures the load, and the accelerometer measures the movement, the motion. That's like, like the static load test. Remember, we measured load and motion, load and movement statically. Now we will measure the same dynamically under each and every hammer blow. So when the hammer impacts the pile top, we put our gauges on the pile. The gauges feel the impact of the hammer, the stress wave as it passes. The stress wave goes down to the bottom of the pile, reflects and comes right back up where the gauges feel it again. So this is a signature of one blow. This is a dynamic test result of one hammer impact, showing the impact at the top of the pile and the reflection from the bottom of the pile versus time. This is more like 20 milliseconds, but it can be resolution by the computer, resolute by the computer. So since we are taking the measurements under each and every hammer blow, we have a complete record of the entire pile installation. If you look on the bottom left-hand side, you will see the number 1,813. This is however many blows it took to drive this pile. 1,800 blows to drive this pile into 125 feet penetration. Then we can group all of these blows into each foot of penetration, because the inspector on site is counting how many blows per each foot of penetration. So each foot will get an average, and that will tell us, and this is the same thing graphically, versus penetration. If we look on the right-hand side, the blue line versus penetration depth is the static load-bearing capacity of the pile, and the red line is the blow count in blows per foot of the hammer. So now we have the relationship of blow count and static load-bearing capacity during pile penetration depth for each and every foot of driving. This information can be used to assess, to evaluate the hammer performance, the pile performance, and the soil performance for each and every hammer blow. The hammer runs at a click of about 50 blows per minute. Let's say approximately one blow every second. One blow every second, the hammer hits a pile to drive it. Between these blows every second, we have all of these results I will describe to you next that have to do with the performance of the hammer and the pile and the soil. So the hammer has a rated energy, a maximum potential energy that is equal to the weight times drop height. Every hammer is rated that way, weight times drop height. That's its potential energy. It will fall and compress a cushion on top of the pile, accelerate the mass of the helmet, compress a plywood on top of the concrete pile, and finally reaches the top of the pile in what we call transferred energy. So the best measure of the performance of the entire pile driving system is by measuring how much transferred energy actually reaches the pile top. How much do you think is the ratio of transferred energy to the maximum potential energy of the hammer, rated energy of the hammer? How much do you think the pile actually receives from the hammer? This histogram is a summary of about 1,000 projects. And you see that can range between 10% to 80%. It could be anything. The mean is 35%. Why is that? Why does it vary so much? And why is the mean so low? Well, that depends on the mechanical condition of the hammers, on the state of maintenance, of the state of mechanical condition of the cushions inside the hammer, and also the plywood that we put on top of the concrete pile to cushion it so don't damage the pile. All of these play together in giving us this high variability. And this is why I was concerned when we talked about the wave equation analysis by simulating the hammer, that we have to have a good measure of the efficiency of the hammer if we have to make sense of its blow count in establishing pile load bearing capacity. It can vary widely. So that's why the measurements are needed for the performance of the hammer. During pile driving, the pile undergoes a very complex state of stresses that includes compression, tension, bending, and torsion. Repeatedly, in the previous case, 1,800 blows it took to drive the pile. To have to hit the pile so many times to get it into the ground at the maximum possible stress level. So having done that, we were curious and we were wondering how did the pile feel about that process of installation, and we extracted this one pile and found it to be damaged. In fact, many of these piles were damaged on this particular project. That is why it's important to take measurements of the load, of the force, of the stress in the pile under hammer impacts in order to avoid damaging the pile top, as we see in this case. And from the pile top measurements, we can follow the stress wave and travels down the pile length, and we can calculate the stress level in the pile at any location X, including the full length of the pile. So now we can calculate how much stress the pile bottom has. When we drive piles to a large end-bearing resistance, a very high end-bearing resistance to a very hard rock, let's say, the stresses at the bottom of the pile could potentially be twice that at the top of the pile, because the stress at the top of the pile in compression comes from the hammer. That compression stress from the hammer travels down the pile length, reaches the pile bottom, and activates equal and opposite reaction, also in compression. Both of these compressions add up to the bottom of the pile and the bottom of the pile, that we can have potentially twice as much stress at the bottom than we have at the top. This particular project, they were driving these steel pipe piles into a very hard rock, and you notice the top of the piles, there's no damage at all, but they thought that they may be driving these piles into different depths into that hard rock, until they realized after extracting one of these piles that they were not penetrating the rock, but they were in fact damaging the tip of the pile due to the doubling effect I just described to you at the bottom of the pile from very hard end-bearing resistance. Here's another case also with damaged pile driven to very hard end-bearing, and you see it in the data. If you look at the data on the left-hand side, the first peak on the left is the impact at the pile top. The second peak on the right is a reflection from the pile toe, and the intermediate little reflection there indicates the reflection from the damaged location in the pile. That's a steel pile damage, and this is a concrete pile damage also the same way, where we see the impact and then an early reflection in the data before the reflection anticipated from the pile toe, indicating damage. So should there be any reflection in the data indicating damage, then from the time of that reflection and the amount of reflected energy, we can calculate how much damage the pile has. We can calculate the location of damage and the amount of damage, whether it's a small crack or a very large damage or complete break. That can be indicated from the measurements at the pile top. Remember, we're doing this for each and every blow of pile driving. So we talked about hammer performance and pile performance. Now we'll talk about soil performance. When the hammer hits the pile top, it forces the pile into the ground. So the hammer hitting the pile top generates a wave, a stress wave to go down the pile. When the pile moves into the ground, it activates soil resistance, activating soil resistance and skin friction and end bearing. These activated soil resistance forces also generate a stress wave in the pile going upwards in compression. So now we have a wave going downward in the pile from the hammer and a wave going up the pile from the soil resistance effects. Depending on where that soil resistance is located at, whether it is in skin friction or in end bearing, it will arrive differently at the pile top. So from the time of arrival of these stress waves at the pile top, the waves going up the pile, we can tell where they were generated in skin friction or in end bearing. We can also take that measured data and further analyze it to see how much dynamic resistance we have and how much static resistance we have at each length of pile. Let's say every 5 feet of pile length, we know how much resistance we have in skin friction and how much we have in end bearing using this CapWeb program. So now, if we know the pile elasticity, we know its length, we know the skin friction resistance along its length and end bearing, we can simulate the static load test. So this is a simulated static load test, load versus movement from the dynamic measurements without having to run a full-scale static load test. So how do these two compare? How do they correlate? There have been numerous studies over the last 50 years on various projects and academic studies that will correlate or that correlated the results of a PDA, CapWeb, dynamic analyses, and a full-scale static load test. So this is one of these ASCE published cases. So this process of dynamic load testing is typically applied on a job site by using what's called a test piles driving program. So the design engineer will select a number of piles for the project to be driven ahead of construction as test piles. The purpose of this program is to drive the test piles, get the information, and come up with production pile length for the rest of the project and production pile driving criteria to install the production piles with. And to also check the engineer's design assumptions and the contractor's means and methods. So a test pile program typically starts with driving the pile and dynamically testing it with the pile driving analyzer, analyzing the data with the CapWeb program, refining the wave equation analysis with the findings from the field measurements, issuing a pile driving criteria relating blow count and the required capacity, and then giving that to the inspection on the job site. The inspector then can apply the driving criteria to the remaining of the piles on the job site. So that is a typical process in which this dynamic testing is utilized in production. However, this process can be expensive, can be time-consuming, not warranted, or ineffective in certain cases. That is why, as an alternative to that conventional application of a test pile program, some projects drive production piles without test piles, but with 100% dynamic testing. This 100% dynamic testing is now required. For example, in Florida, the highway department requires that each and every pile they drive on their projects be 100% dynamically tested. The benefits they found to that to be it optimizes construction efficiency and economy, and it increases engineering reliability. Increasing engineering reliability means that if the design engineer knows that each and every pile has been tested and verified for capacity and integrity, then the design can utilize a much more efficient foundation. In other words, a much lower factor of safety would be needed as opposed to not knowing all of that information. The contractor also have found that having 100% testing without having to do a test pile program makes the project more efficient and more economical and faster to do. So that's a new trend now in the pile driving foundation industry. In the flip side to that, however, one must determine production pile length beforehand. So without the benefit of a test pile program, the design engineer must come up with production pile length, because when we say 100% testing, then all of the piles will have been preformed and shipped to the job site to be driven and tested at once. So one would have to predetermine a production pile length beforehand, which can be tricky in many situations. Some projects actually utilize both a test pile program and 100% testing. And this is one such projects that utilize a design build, test pile program, and 100% testing. And according to the design build manager for this project, it is one of the best pile driving jobs I ever had, because they have the best of both worlds, the advantages of a test pile program and the advantage of 100% testing. So that was driven piles aside of the deep foundation group. Now we will move into the cast in situ deep foundations, starting with auger cast piles. Auger cast piles are used typically on buildings, but now more recently on bridges as well. So auger cast piles has now become an alternative to driven piles as a deep foundation solution. This is a typical view of a auger cast installation rig and the various components of it. And this is the process an auger cast pile is constructed with. It relies on a continuous flight hollow stem auger. So this auger has a hollow stem in the middle of it and continuous flight. So the design engineer decides how deep we should auger this hole to. And then once we reach the depth, they withdraw this auger, and then they push the grout to the bottom of the hollow stem and fill it with grout. So by the time the auger makes it all the way up to the top of the ground, the hole has been filled with concrete with grout. Then they push in a steel cage into it. So this is a conventional way of of constructing an auger cast pile. Alternatively, at the bottom of the stem of the auger, they may change the direction of the flights, which means that now when we are augering this into the ground, we're pushing the soil sideways and we're not mining the ground. We're not taking soil out of the ground like we did previously, but we're actually pushing it, displacing it in the ground. So these are called a displacement type auger cast in situ piles. Inspection of these installations, the old way, this inspector, as you can see, is doing the inspection with his foot. What he's doing is he's counting the number of strokes of the pump that is delivering the grout into the pile versus depth. So he's counting how many strokes of grout the pump is delivering versus every 5 foot of penetration of the grout into the ground. And then he can establish kind of a profile of grout versus depth. Of course, there are many things wrong with this antique process. Now, these rigs rely on automation. So we automatically now, we measure the grout volume versus penetration depth and the pressure of the grout that will tell us that we have a good, well-constructed auger cast pile in place. Drill shafts, on the other hand, are constructed a little differently. They're constructed by drilling a hole into the ground, putting the steel cage in the hole, in the empty hole, and then pouring concrete in the middle of that steel cage that will then make its way to the side wall and fill up the shaft. So that's a drill shaft construction. Drill shafts have many advantages. They come in very large sizes at times, 10 feet or more, 100 feet or more in depth. They carry very high loads, compression and lateral. So if we happen to be lucky enough to have a site where the water table is very low, then we can simply drill the hole, look down it, put the steel cage and fill it with concrete. So that's an easy construction of a drill shaft situation. However, if the water table is high, then we have to use other means, such as using maybe a steel casing. It could be a temporary or a permanent steel casing in the ground to make that shaft, or we can use slurry. Slurry is a very thick liquid fluid material that is put in the hole to exert lateral pressure, hydrostatic lateral pressure against the pressure of the wall of the hole in the ground so it doesn't fall in. So that's how we maintain the hole during the construction of the drill shaft. We construct this drill shaft with the concrete from the bottom up. For that, we use a very long semi pipe. So we have this pipe that starts at the bottom of the hole. We put concrete and the hopper up on top, and we lift the pipe. We lift it as we make that shaft. Of course, we cannot lift it too fast and be above the concrete. Otherwise, we may have an issue with the construction of this shaft. The steel cage design have to be done properly and appropriately. Properly in order to provide the structural strength of the shaft with the reinforcing steel, and appropriately in that it has to allow the concrete to make its way outside it to engage the side of the hole in order to have our geotechnical skin friction for this drill shaft. So the opening and the design of the steel has to have enough openings to allow the concrete to flow through it and engage the side of the shaft. Of course, a steel cage like this would not be good because it will not allow the steel to ooze through it, to pass through it, and engage the side to give us the geotechnical resistance we need. Concrete is the same way. It has to be designed with enough strength, obviously, to carry the load, but it also has to have enough workability. It has to be workable enough to pass through the reinforcing cage openings and engage the side for geotechnical resistance. Sometimes it's so bad that it just doesn't make it out, and therefore this shaft will have a problem in its integrity outside the cage and also the geotechnical shaft resistance capacity. So when we drill the hole, we have to inspect it for a variety of purposes. Number one, we have to inspect the hole for profile. We have to know if the hole is the right dimension, area-wise, and also for verticality. We have to make sure that the hole is plumb, because the drill shaft, the hole in the ground has to be plumb within a small tolerance. Remember, we're drilling this hole like 100 feet in the ground, and we don't want it to be off plumb by too much. At the same time, we have to test at the bottom of the hole if we have any debris, if we have any loose material, because we are counting on end-bearing resistance of the drill shaft when we pour the concrete. All of this before we put the steel cage and before we pour the concrete. We have to do these inspections, these tests. The profile and verticality are done with this equipment called the shape equipment that is sent down the hole, even with a slurry in it, and then it sends signals and waits for reflection from the side and gives us a profile of the hole in the ground. And then it also measures the verticality of that hole to make sure that everything is within tolerance. The bottom cleanliness of the hole can be inspected with this device called squid. It has 3 little probes that are sent down to the bottom, and the probes will measure the thickness and the strength of the bottom of that drilled hole to make sure that the debris thickness and strength are within tolerance. Otherwise, the hole has to be cleaned before the steel and the concrete are introduced in it to make the drill shaft in place. So after we do all of that, the shape of the drill shaft and auger cast pile may be perfect, perfectly cylindrical, great, well done. Maybe they can be a little bit off, maybe they're okay, but at times they can be very bad. So the integrity of them could be bad because of a variety of reasons having to do with construction, the ground conditions, etc. So there have been many, many studies done by universities, by highway departments, by owners that show somewhere between 20 to 50% of all of these cast in situ foundations have some kind of a structural issue. So therefore, we have to test for integrity of these cast in situ elements. The factors affecting the shape of these elements and integrity underground have to do with the geotechnical conditions, the design itself, and I mentioned the reinforcing cage, for example, the concrete, installation means and methods that the contractor uses, and the workmanship of the contractor. Very important to have a good product. Integrity testing checks for flaws and defects. A flaw is a deviation from the planned shape or material quality. A defect is a flaw that is so bad that it will affect the performance of the shaft or the durability of it. The easiest and the most expedient and the least expensive way to inspect for integrity, to test for integrity, is by low strain testing, pit testing. Low strain pile integrity testing, ASTM designation D5882. This test simply is based on putting a sensor on top of the pile of the shaft and hitting the top of the shaft with a small handheld hammer, sending down a low intensity, low strain stress wave that goes down to the bottom of the shaft, reflects and comes back. That tells us that the shaft is fine. Should there be a defect at some location in the shaft, that defect will send back an early reflection. So the engineer here is testing the shaft at the shaft top, and then we see the impact, the stress wave goes down and reflects from the bottom of the shaft 25 meters long. No problem with this shaft because there's no early reflections, compared to this shaft that has an early reflection of it at 15 meters depth. So this shaft has a defect because it had sent back an early reflection before that anticipated from the shaft bottom. Depending on the location of this defect, on the location of this reflection, and the amount of energy reflected, we can simulate that by signal matching and estimate the location and the amount of this defect from these pile top measurements. So this is a very simple way to test the shaft, although it has many, many limitations having to do with the size of the shaft, the length of it, the diameter, the resistance, and the type of defects that can be obtained. This same test can also be applied to test for unknown foundations, testing of piles under existing structures for unknown length. Another test that is typically done to evaluate the integrity of drill shafts or auger cast piles is the cross-hole sonic logging, CSL testing. Also, it has an ASTM designation D6760. This test consists of casting into the shaft, connected to the steel cage, access tubes, 1.5-inch steel access tubes, distributed along the circumference of the shaft. The number of access tubes needed is equal to the diameter of the shaft in feet. So a 5-foot diameter shaft requires 5 of these access tubes. So the access tubes are cast into the shaft, And then we take these access tubes after we put the concrete and we wait until the concrete cures and hardens. And then we take these access tubes two at a time and we send a transmitter and a receiver into them and we lift them up and we scan between these two tubes. Then we take these two tubes two at a time, the 4 or 5 tubes two at a time, and scan the entire volume of concrete between the reinforcing cage bars. The number of scans we can do is dependent on the number of tubes, and the formula is n squared minus n over 2, where n is the number of tubes. So for a 5-tube shaft, we can do 10 different profiles, taking the tubes two at a time. So we can scan all of that volume of concrete in between the access tubes inside the reinforcing cage. So if we have good concrete, then the signal sent from the transmitter is received by the receiver well at a predictable time. However, if we have a defect in the concrete at some location down the shaft length between a certain tube pairs, then that defect, being a bad concrete or a void, will delay the signal. So good concrete will send good signal, and a void or a defect will delay and weaken the signal as it's being received. And remember, these signals are being sent and received all throughout the entire length of the shaft between these two tubes. So we can stack these signals on top of each other and show the results for the full pile length. So on the left-hand side, we show the result of one scan between these two tubes versus length. It shows very good signal reception. In the middle, we see data that has a signal loss in the middle of the shaft. And on the right-hand side, we see a signal loss at the bottom of the shaft. And this is how we evaluate this test result. We can then put all of that information in a 3D tomography program that will tell us the defects in the body of the shaft versus depth and quadrant and location within the cross section of the shaft from these different scans of the various tubes. Testing has to wait until the concrete has cured. That may take, a week, 5 days or a week or so. So the contractor has to wait. The shaft cannot be tested until, quite a few days, 5 days or a week have passed. Sometimes there's debonding between the concrete and these access tubes, which may give us false signals or a bad test result. The test can only check for defects within the body of the shaft inside the reinforcing cage. And this is a test study where we put styrofoam inside the concrete of the shaft in between the access tubes inside the reinforcing cage, and then we can see the loss of signal. But if we have a defect outside of the reinforcing cage, the signal will not be able to see it simply because it's in between the reinforcing cage. So this is another limitation of this test. It can only test for concrete inside the reinforcing cage and not outside it. The newest method and the most comprehensive method of evaluating the integrity of drill shafts and auger cast piles is by thermal integrity profiling. This method relies on the measurement of the temperature created by the heat of curing of the concrete in the ground. We know that when concrete cures, it generates heat. So what we're trying to do here is to measure the temperature of the concrete inside the shaft versus depth. And from these temperature measurements, then we will establish the integrity of the shaft. ASTM standard D7949. This is done by stringing thermal wires with thermal measuring devices every foot along the length of the shaft and tied into the reinforcing bars. Similar to before, the number of thermal wires needed is equal to the diameter of the shaft in feet. So a 4-foot diameter shaft will require 4 of these wires strung along the length of the shaft tied to the reinforcing cage. Temperature readings are taken every 15 minutes from the moment of casting, all throughout the curing process to peak temperature and beyond, which may take a day or two. So it may take 24 to 48 hours, depending on the size of the shaft, to reach peak temperature. There's no testing engineer needed on site. The data is taken automatically, sent to the cloud, and the engineer in the office can follow the maturity, the temperature development in the shaft while it's curing. And these are pictures just showing how these thermal wires are tied to the reinforcing cage. So we're now taking temperature measurements along the length of the shaft and around the circumference of it. If all of the temperature measurements are read equally, then the shaft must have equal volume of concrete, or the shaft has good integrity. A localized defect will produce a localized reduction in temperature at that location, at that depth, and at that corner of the shaft. Furthermore, if we compare the temperatures along the length of the shaft against each other, opposite each other, if one side consistently shows a higher temperature than the opposite side, that means that the steel cage had shifted inside the concrete, shifted so that the one side is closer to the center of the concrete where it's hottest, and the other side closer to the soil where it's cooler. So from these temperatures, then, we're able to tell from the localized reduction of temperature and the comparison of temperature if the concrete is solid or if we have a defect, and if the steel has shifted inside the concrete throughout the length of the shaft, throughout the cross-sectional area of the shaft. So this shaft here shows a reduction of temperature, and it has 10 different wires, which means it's a 10-foot diameter shaft, and it tells us that wire number 7, 8, and 9 at a depth of 90 feet, they show a reduction of concrete, a reduction of temperature. And from the shifting of the temperature, we're able to draw a 3D diagram of the shaft showing the concrete profile, showing the defects, and the steel inside the concrete shifting profile. This is important for the evaluation of the integrity of the shaft, the load-bearing capacity of the shaft, and the longevity of the shaft. Because if we know that we have lost the cover, if the steel had shifted enough and we lost enough concrete at a certain location, then that steel may corrode, so the longevity of the shaft may be in question. And this is showing you how we make the transition from temperature measurement to concrete equivalent, to concrete or cross-section equivalent by ratioing the temperature and the temperature along the length of the shaft. The same thing can be done for auger cast piles. Auger cast piles, sometimes they do not have a reinforcing cage for their full length, but they do have one steel bar throughout the length. So by taking measurements on that one steel bar inside the auger cast pile, we're able to evaluate and to establish a profile area versus depth of that auger cast pile. The same technology of thermal integrity profiling has been applied to also diaphragm, steel reinforced diaphragm concrete walls. So we talked about low strain integrity testing, right? We can hit the top of the shaft with a small hammer and evaluate its integrity. This will tell us something about the integrity, but nothing about the load-bearing capacity. Because to evaluate the load-bearing capacity, we have to move the shaft. We have to move the shaft to activate resistance in order to calculate load-bearing capacity. For that, we have to apply high-strain testing. To do high-strain testing, we need a much bigger hammer. So we need to have a hammer big enough to actually move the shaft to activate soil resistance to calculate load-bearing capacity. Just like we did with the pile driving with the hammer, but when we are constructing the drilled shaft and the auger cast pile, we do not have a hammer to drive them like we do with the driven pile. We have to bring in a drop hammer. The size of the drop hammer, depending on the size of the shaft and depending on the load we're trying to test for. The weight of the hammer is typically 2% of the ultimate load we are testing to. Same thing with the driven pile. Now we have a drop hammer on the auger cast pile or the cast in situ drilled shaft. We bring the hammer, we hit it with the shaft with it. We move the shaft, activating soil resistance, and we measure with the pile driver analyzer and the CapWeb program the wave going down, the wave going up, and we do the normal analyses I showed you earlier that will simulate the static load test that we do not have to run a full-scale static load test. So this is a full-scale static load test using top-down measurements, top-down loading. We need all of this dead weight, all of this reaction, so we can put the hydraulic jack on top of the drill shaft and apply the load for a static load test. This is how we perform conventional top-load static load testing. Very involved and very expensive. And I may add, it could be dangerous at the same time. What if we try to do it a little differently? Instead of putting the hydraulic jack on top of the shaft, what if we were to put the hydraulic jack at the bottom of the shaft? And then we load it bidirectionally. We push up on the shaft for friction and down for end bearing. So instead of shaft top, static load test, load bearing, we static load test the shaft from the bottom up using a bidirectional load test. There is actually an ASTM standard for bidirectional load test as well. So by putting the hydraulic jack at the bottom, then we do not need to have any reaction up on top. We just have to, this engineer here is performing the static load test, full-scale static load test, and there's nothing on top of this drill shaft. We use it bidirectional loading. So by putting the hydraulic jack at the bottom, we push up and down at the same time. We load the top and use the bottom as reaction and vice versa. So when we apply that load, we measure how much load we apply and we measure the corresponding shaft top movement, moving up in friction. And at the same time, we measure how much it moved down in end bearing. And we apply more load and we see more movement up and more movement down. And we apply some more until one of the two fails. Either the skin friction will fail or the end bearing will fail first. At that time, the test is done. So therefore, the maximum load we can load the shaft with using this procedure is equal to twice the weaker of skin friction or end bearing, because we need one to load and the other as a reaction against it. So once of them reaches its maximum resistance, then we cannot load the other one against anymore. So this is a typical bidirectional static load test plot showing load versus movement upwards for friction, downwards and end bearing. We can take this information of load versus movement upwards and downwards, friction and end bearing, and convert it into an equivalent shaft top static load movement graph. From these measurements at the bottom, we can simulate, without having to do so, without the need for reaction up on top of the shaft, we can simulate a shaft top load versus movement from the bidirectional bottom measurements. This type of testing has allowed us to load foundation units, deep foundations, to loads unheard of before. This bridge in St. Louis, for example, is founded on drilled shafts, 11 feet in diameter, with 23 feet rock sockets into the rock. And utilizing this bidirectional load testing, one of these shafts was tested to 36,000 tons. Can you imagine loading 36,000 tons with top loading? That would be tremendously expensive, unsafe, and very time-consuming and extremely expensive. All of the procedures I described to you today, all of these testing and analyses and inspections I outlined to you today are widely available in standards, in codes, and specifications, and textbooks, and the conference proceedings, etc. So there's no shortage of information about all of these tests I outlined to you today. I want to have a friendly reminder to you that there are scholarships and grants available to you as students. So please apply. There is money waiting for you at the DFI, Deep Foundations Institute. My company, for example, there are many scholarships available. One of them is my company's scholarship. If you can look it up, please apply. And ADSC, the Association of Drill Shaft Contractors, they also have lots of scholarship and grant monies available and ready for you. So should you be interested in this field of deep foundations, please consider and apply for these scholarships and grants. My company, GRL Engineers, we have offices throughout the United States. Should you be interested in this field of deep foundations, deep foundation testing and evaluations, please consider us for employment. Once you graduate, reach out. This is a website, and we are always looking for good engineers and good students for employment. With that, I think, Noah, we have 5 minutes left for questions. I'll try to answer all what we can within the time. And here's my email address, very easy to remember, mhussein@pile.com. Please reach out in case you have any questions later on, or if I can be of any assistance to you in any way I can. With that, thank you for your attention, and I think we may have a few minutes for questions.
Yeah, thank you. Thank you very much. The presentation was great, and I really loved all of your experience and all the background in it. I really felt it, and it was really appreciated.
Thank
But
you.
yeah, we've got a good couple minutes for questions for anybody online or in person. Go ahead, Tanner.
Thank you so much for your presentation.
Thank you.
One question I have is that, so we went through all these evaluations of all these drilled shafts and pile foundations. In your experience, have you ever worked on a project where when you tested one of the piles and it failed, well, what did you do to solve that issue? Did you have to just drill another pile somewhere else, or how did that affect your project?
Thank you for your comment and an excellent question. So the answer is it depends. It depends on whether the shaft or the pile had failed geotechnically. In other words, it did not have enough resistance, or if it had failed structurally. In other words, does it have a structural defect? If it has a structural defect, then it depends where and what defect it has along its length. Is the defect closer to the top? Is it closer to the bottom? And what kind of loading this pile or this shaft is supposed to support? Is it only supposed to support vertical axial load? Is it supposed to take tension load? Is it supposed to support lateral load? Will determine if it's good enough or not, and what kind of damage or defect it has, and where the defect is in combination to the loading requirement on it. It may be okay. If it's not, then what they do sometimes is if they have to fix it, they may core. By coring, they core down a hole down the shaft and they pressure grout the defect if they can get to it. That is why the thermal integrity profiling is so nice, because it tells you what corner of the shaft the defect is in and how deep. So they can pinpoint it, and they can core and grout to it. So sometimes grouting will solve a problem. If nothing works and everything fails, then they replace the shaft by putting in another one. If the shaft had or the driven pile had failed geotechnically, that's kind of an easier fix, because all you have to do is to drive it deeper or drive more off them. You just adjust the design then.
Gotcha. Thank you so much.
You're welcome.
All right. Anybody else with questions? Go ahead, Alejandro.
Thank you very much for your presentation. I would like to ask about the last slides about bidirectional testing. Is it also called O-cell? And the curves that go upwards and downwards should be approximately the same.
Yes.
What would I interpret if they are not? The test was not performed properly? Or what would I interpret?
Correct. So thank you for your question. Yes, it used to be called the O-cell after the person who invented it, Professor Osterberg at Northwestern University. Professor Osterberg invented this test and had a company and a patent on it. But the patent had since expired. Since the patent had expired, many other companies now make these cells and perform the test, including my own. My company does that, and many others. I'm not the only one. So many companies do that. So they do not refer to it as the O cell anymore. They refer to it as a bidirectional load test. So that's the first answer, the first part. The second part is you are applying equal load, right? Because you're applying it with a liquid, and the liquid gives you the same pressure upwards and downwards. So you're applying the same load upwards and the same load downwards equally. The reaction is not the same, though. Depends on the stiffness and the resistance. So just because you're applying equal load does not mean that you'll get the same displacement upwards and downwards. The same load will give you different displacements upwards and downwards, depending on how much resistance you have upwards in friction and the stiffness, and how much resistance and stiffness you have in end bearing below that load. So equal load does not necessarily give you equal displacement. That's what, in fact, we're trying to measure. We're trying to measure how much displacement these loads will give us, both in uplift and in upwards and downwards, in friction and in compression. I hope I answered your question.
Thank you.
All right. I think we got time for one more question. I'm going to be honest, I do have a question, so I'll come around where you can see me. Again, thanks for the presentation. I'm curious about, on the one case where it was trying to drive a pile into an extremely strong rock. Have there been cases with extremely strong rocks where, like, my initial inclination is to find some kind of pile that we could almost like point like an arrowhead in some way? Have there been cases where that happens, or do you just get an even larger pile and push even harder?
Well, an arrow, a pointed tip will actually make it worse because you have less area, so therefore you have more stress at the bottom. What they have is they put a reinforcement at the bottom. They reinforce the bottom sometimes and try to push through it. But there's no need to drive through that hard a rock like this. We'll do this with a steel. So you have reached the maximum load now. Yeah, what the controlling resistance in this case is not the rock, but the pile itself. So if you need more load, then you have to have a larger pile or the same size pile with more wall thickness, more area. So basically a heftier pile.
That same solution, even if you want to push through that layer, it would still be the same, just a heavier
Correct.
pile.
Correct.
Okay.
Yes. I should. You're absolutely right, and I stand corrected. This applies to piles driven to rock or through hard layers, trying to reach deeper. Same applies.
Okay, I see. Any other last minute questions? Well, if not, he had his email at the end, and I'm sure he's happy to. But otherwise, let's give one last round of applause for Mohammed.
Thank you. Thank you for your time. I hope you found it interesting and useful.
Absolutely. All right,
Very
with that, everybody, thank you so much.
Thank you. Take care and stay in touch.
All right, will do. Thank you.